Welcome to Coherent Solutions quick tour of the BERTPXIe 1005/1003. Throughout the presentation I'll refer to the BERTPXIe 1005-4 and 1003-4. They're really the same instrument except the 1005-4 comes equipped with two sets of 8-channel cables. The 1003-4 does not. The BERTPXIe 1003-4 is a single-wide PXIe module. There are 4 channels of differential outputs from the pulse pattern generator, and if the synthesizer for the PPG is built in, there's no need for external clock generation. There are 4 channels of differential inputs on the error detector, each with its own clock data recovery. Data rate is supported from 1 to 14.5 gigabits per second continuously with non-return to zero format. The front panel is a high-density front panel coaxial connection solution with all 16 connections on the front. The error detector also supports I-mode and bathtub error analysis. The PPG also has precursor and postcursor emphasis on its outputs. Equalization on a receiver can be adjusted. Multiple units can be synchronized via the PXIe backplane. Because the BERTPXIe 1003 is a single-wide PXIe module, it's possible to put up to 17 of these modules in a single large PXIe mainframe. That's up to 68 channels of bit error detection at 14.5 gigabits per second. With MXI extenders, you can extend these to 2, 3, 4, 8, even 10 different mainframes and literally have hundreds of channels of bit error rate testing. The PPG outputs and the error detector outputs, each with 8 conductor solutions, utilize a high-density solution from Rosenberger on the front panel side. There are breakout cables with less than 2 picosecond skew matching on all 8 of the connections on each of these breakout cables, and they support SMA, which is also compatible with 2.92 millimeter interfaces. There's also an 8-channel to 8-channel loopback cable as well. For the scope, screenshots, and the user interface examples will be shown in this presentation. Here's a diagram of the setup we have. We're differentially going to drive an evaluation board with an LR for a transceiver on it, and we're going to be using the BERTPXIe 1003, just one of its channels for that. We're going to be running this signal through a passive optical demux because this actually has 4 wavelengths as an LR4 transceiver, and we're just splitting off the 1300 nanometer portion of that. The signal will run through a variable optical attenuator, and that is going to allow us to reduce the signal level in order to intentionally induce error rates. But the actual optical signal is being converted with our analog ODE converter known as the O2E PXIe-1001. That is what's single-endedly driving the channel 2 of the error detector in this setup. And of course we also have an SMU from National Instruments which provides a 3.3 volt supply to the evaluation board. If you're curious about the actual instruments used in this setup, it's the ODE PXI-1001 is our analog ODE converter that's driving the error detector. We have a passive PXIe-1004 to split the 1300 nanometer signal off. We have the VOA PXIe-1002-2 is our attenuator, and of course our BERTPXIe-1003-4. And to round it off, the epic scope is what is going to be showing the analog waveforms that are coming out of the pulse pattern generator. Let's look at the pulse pattern generator part of the BERTPXIe first. Under the PPG menu, the first thing I'll do is enable channel 1, and you can see in the amplitude here you can either type in an exact value for the amplitude, goes all the way up to 1.1 volts differential. The actual signal is single-ended as half of this value, and as I change the value here you can see on the scope the amplitude change. So 500 millivolts differential is 250 millivolt single-ended signals. I'll set that to 800 millivolts there. Now if you really want to see the actual signals, especially when I get to the pre and post cursor, let's change this to a divide by 4. You can see there's all the way up to PRBS 31 here. This divide by 4 allows you to see that they're skew matched and that they're actually opposite polarity. And so mathematically, if you subtract the two signals with these two 400 millivolts, you're going to get an 800 millivolt differential signal here, and there you see it. Okay, next we're going to take a look at the pulse pattern generator output. But first I'm going to set my clock here. You can divide it down by 16, which is the appropriate thing to do if you're directly triggering a scope. Now if we go to the PPG, you'll see that if we put this on divide by 4, it will be much easier to see what's happening with the pre and post cursors here. I've selected precursor or post cursor, and let's put 3.5 dB, and as you can see it puts a small peak after the rising and after the falling edge, and as I increase that, it increases the overshoot and the undershoot relative to the high and low stable levels. If you change this to precursor here, and let's put in a nice little 3.5, then the aberration or the undershoot comes just before the rise time and the overshoot comes just before the fall time. So those are two opposite effects that you can play around with in order to compensate for cable loss and equalize your coax loss. Next, let's take a look at the error detector menu. So here on the error detector menu, we're going to start the error detector because we have PRBS 31 on the pattern and the error detector. And as you can see, it's going to start accumulating errors here, and we're going to go over and reduce the optical power. As we do that, you'll see that as the bits are accumulating, there's no errors in the error menu, and you're getting a flat line for channel 1. But eventually, as we reduce the optical power enough, you should start to see some errors, and there they are. And so now we can reverse the optical power and go back up. But since we're collecting the accumulated number of bits, you can see the instantaneous bit error rate calculated from that is being presented. And this is basically your accumulated and or your instantaneous error rate menu here. Up next, we're going to take a look at the phase and voltage I measurements in the I menu. So here I'm going to change the data rate to 8.5 gigabits per second, so we have a nice clean I here. And as you can see, I'm going to go open up the optical attenuator, and I'm going to set this to constant power, and we're going to start this off at approximately -1 dBm. So the I is very open here. I'm going to change the increments to 1 dB so we can move 1 dB at a time in power. And as I reduce the power, you can see the I on the oscilloscope collapsing. So this is the actual analog I that we're going to be using for testing the error rate measurement, as well as the I and the bathtub curves later. So as I keep reducing it here, I'm changing the scale on the scope so you can actually see it's at 50 millivolts per division right now. And we're getting down to about 60 millivolts peak to peak. We're going to change that to 20 millivolts per division, and as you can see, I can continue to reduce it, and at -10 dBm this is going to be close to the sensitivity of 25 millivolts differential here. Keep reducing it here down to -10, and there you see the I has collapsed all the way down to close to 40 millivolts peak to peak there, even less than that. And as you can see, we can reduce the I well below sensitivity levels there. Now let's go to the I menu here, and we're going to start the I, and as you can see we have -3 dBm, so it's quite open here. And if we adjust the power, I'm going to reduce the power, which will reduce the I opening. Let's set it down to -6 dBm. Run the I scan again, and as you can see the I is closing. Now you can change the resolution to have it all the way down to 7 millivolts vertical and 0.0156 UI horizontal. We run that again, and you can see that there's much better resolution on the I there. And you can kind of see down to -10 to the -4th error rate. If I continue to reduce the power, let's take this down to about -9 dBm here and run the scan again, and you'll see that the I is almost completely closed there. Next, let's take a look at the bathtub curve measurements under the error detector. Okay, for the bathtub measurement, we're going to actually increase the optical power so we have quite an open eye. Bathtub is a funny name, but really what it's going to do is show you the phase noise on the horizontal. So let's change to the bathtub menu here. And so if we run it on channel 1, it's very quickly going to do a scan of the error as a function of the offset of the phase, and you quickly get what is called a J2, J9 measurements. Let's go ahead and reduce the optical power, and you'll see that this bathtub, or the opening, is starting to close down because of the power reduction in the eye there. And so if we run this one more time, you'll see that the bathtub curve is starting to close and becoming smaller and smaller. So those J9 jitter values are becoming larger. If we reduce this even further to -9 dBm, I think what you'll see is that the intersection is starting to happen at the J12 here. Let's run the bathtub curve one more time, and there you can see it's starting to intersect at J12. Thank you for watching the presentation. This is David McCormick, Coherent Solutions Technical Sales Manager for USA.